So we're going to go through the solution to the homework problem from the Knight textbook, Chapter 3, Problem 33. And we've already done a problem very similar to this in class. It was the water sprinkler problem that we did last week. So I've already written out a solution, and I'm just going to run through it quickly and emphasize a few things. So I have a diagram here showing a kangaroo. The kangaroo jumps, and we're given the launch angle of the kangaroo relative to horizontal, and we're also given how far they go in the x direction before they hit the ground, and what we're supposed to figure out is what was their launch speed. So on my diagram I'm showing the initial velocity direction with its angle. I'm also showing the final velocity. Right before the kangaroo hits the ground, he'll be moving down and to the right, and the acceleration vector at all times is straight down because that's a free fall problem, and there's my coordinate axes, x and y. So we need 5 knowns, and because it's a projectile problem, we know ax is 0. We know the vertical acceleration. In this problem we're given delta x is 10 meters. We're told that the kangaroo lands back on the ground, and we know it's level ground. So that means delta y is 0. There's no change in vertical position. And we're also given the angle of the kangaroo's initial velocity. So we have 4 knowns that are x and y knowns, and then we have a known that's the angle, which is neither x nor y. So what we're going to have to do to use our DVAT formulas is make a vector diagram for that initial velocity separate from the picture, and we're going to find the components VIX and VIY in terms of that angle that we're given. And it'll also be in terms of the initial speed VI, which we don't know, but that's okay because that's what we're going to solve for. Alright, so VIX is VI times the cosine of that angle, and VIY is VI times the sine of that angle. Alright, so like we usually do in a projectile problem, we're going to solve for time first. We're going to use the x knowns this time. Delta x is VIX times t. VIX we know is the initial speed times the cosine of that angle, theta. So that's VIX times t. So time must be delta x over VI cos theta. We know delta x, we know theta. We don't know VI yet. What we're going to do is use that expression for time and sub that into our vertical DVAT equation. So for the vertical variables, we know delta y, which is 0, and we know ay, and we're going to use that time as our third known, and plug in from our x equation. Again, we have a formula for time. We don't know the number yet. All right, we're going to plug that into our vertical DVAT equation. So we have delta y is VIYT plus 1/2 AYT squared. This is simpler than it looks because delta y is 0. And so what I'm going to do on the right-hand side is factor out t to get t times the quantity VIY plus 1/2 AYT. And that times that quantity in parentheses must equal 0. So either t is 0, which is not the solution we want, or this thing in parentheses is 0. So in that case, we know t. If I solve this in parentheses for t, I get t is negative 2 VIY over AY. And I'm going to just substitute in for VIY, VI sine theta. So I have t equal to negative 2 VI sine theta over AY. And then I also have t is this from my x expression. So the next step is going to be to set those equal. All right. This is time from my x expression, and this is time from my y expression, and they must be equal. And what you can see is we've eliminated the unknown time. If we found something from both the x and y equations, we solve for time and set them equal. So now the only unknown is the initial speed vi, and what we can do here is cross multiply these fractions, and you'll find this expression. And then we're going to sub in our numbers for delta x, for ay, for the initial angle theta, and we find the initial speed to be 12.3 meters per second. And then the problem also wants to know the horizontal velocity. Well, that goes back to our vector diagram. Vix is vi cosine theta, and that comes out to be 11.6 meters per second. There was one more question on the assignment which asked you to find a second launch angle that would give the same delta x and using the same initial speed. Now if you go back to our algebra up here, another way to write this, if I solve for delta x, is if I multiply vi cos theta to the right hand side, I can get this formula, which you've seen before in class. We talked about the range formula. When I have a projectile that has a vertical displacement of 0, this would be the range, which is negative vi squared sine of 2 theta. Right? This 2 sine cosine theta by a trig identity can also be written as sine of 2 theta, and I have to divide by ay. So what you can think about here is the range will be the same, and we're assuming that the initial launch speed is the same, and ay is the same. So the range will be the same as long as sine of 2 theta is the same. So we found one solution where theta was 20 degrees, so this would be sine of 40 degrees because I have sine of 2 times 20. Well, if you think about your sine function, we know that for any angle x, sine of x is equal to the sine of 180 degrees minus x. That's a symmetry of my sine function. So that means I can put in to my range formula back here. All right, I can put in theta is 20 degrees, and I'll get a certain range. Or I can put in, I need to put in a different argument that's 180 minus 2 times 20 degrees. Because the sine of 180 minus anything is equal to the sine of that thing. So that's what I've done here. I've got sine of 180 minus 2 times 20 degrees. And so now I'm going to solve that out for a different theta, just doing the algebra. So let's see. I've got to solve for this angle here, which would be 180 minus 2 times 20. And let's see. Well, I've done it one way here. I've actually gone back to solve for the delta x to put in the numbers. But a simpler way to do this would be just to call this angle here, let's call this beta. And I want to know beta is 180 degrees minus 2 times that theta initial. Well, that's 180 degrees minus 2 times 20 degrees, which is 140 degrees. Now beta would be twice the launch angle, so the launch angle would be beta over 2, which is 70 degrees. So what this means is that if you can launch a projectile with the same speed from two complementary angles. Notice that 70 degrees is complementary to 20 degrees, and they will both have the same range. And we'll see that in class. I'll show you that with an animation. So the second possible launch angle was 70 degrees for this problem.